Okay, so in this short video, I want to discuss MolCalc and how you can build molecules and model them using some molecular mechanics and some modeling software. So you've clicked the link and it's taking you to Better MolCalc that takes you to this website. And then you will see that you're able to construct molecules on a page that looks something like this. So you have the screen here where you have little molecules. So if you click on it, you can look at it, and then you can build using different atoms. Then you can build your molecules. So let's say, for example, we want to build. There's different preset molecules that you can build. So you can build benzene, for example. But let's start with the methane, and let's say we want to build our acetone, which is one of the molecules that you want to look at. So we want to build acetone, and we need a carbonyl in the center one, and then you can add a double bond because that needs to be a double bond. I just need to make sure that I actually click on there. You see sometimes it is a bit unresponsive. There we go. Okay, right. Oops. Control Z. We can just delete. A good time to show you the delete feature. Just wipe it out. Okay. Now you click back there. Okay, so you see that. So once you are satisfied with what you've built, then you can click this optimize button. And this optimize button will then have optimized your structure. So you might have seen previously that that bond was a bit skewed in a different direction. And you can build all your different structures like that. Let's say, for example, you just want to build the acetonitrile. So acetonitrile is like that, and we want to make a triple bond there. Why is it struggling this today? Oh, there we go. Optimize. You see it will optimize to the linear structure like that. Okay, but let's go to acetone because that's the example I have open at the moment. I don't want to do that. I want to add an oxygen there. Oops, what's going on here? Okay, oxygen, double bond. We optimize. There we've optimized. Okay, you're happy with the structure. You've clicked optimize. And you say calculate properties. You say indeed. As long as you're happy. And you're going to do this for all your compounds. And then it's going to take you to a page that's going to give you a bunch of different things that you can look at. So for free energy, vibrational frequency, molecular orbitals, polarity, and solvation. You can look at all these different aspects later on in the computational prac, but for now you're just interested in the vibrational frequencies, because here you can visualize the vibrational frequency modes, which is exactly what we want to do. Okay, so from here the question asks you need to identify the 4 most prominent, strongest stretches in your experimental IR spectra of each compound and compare them, the experimental frequency value with those calculated by the MolCalc app, and then you need to fill in this table. So let's first identify our 4 most prominent peaks. So of course those 3 are quite prominent, and then it's between those 2. So let's say that one and those 3. I've just decided, just for here's. You can pick that one and those 3. It doesn't really matter. It's about whatever. So I mean, these 2 are sort of equivalent. You can choose either or. I mean, it's not really about that. It's more about just going through the process. Now we need to identify what these peaks correspond to. So then you go to the other table in your prac guide, which is the table of that table, the one I want. So for example, you see carbonyl stretches are in this 1700 range. Let's see what that is. Let's add a data label. Come on. Let's format the data point. Man, format the data label. Oops, wrong. It always happens. Just calm down. See, even I still make small mistakes. Let's see the X. Okay, so this is 1725. In other words, this is our carbonyl stretch. Okay, so let's go back to this. we're looking at around about 1000, but the closest one is that one. Okay, it's not that one. We click on to visualize. Okay, that is the carbonyl stretch, which checks it's not that one. So that's the carbonyl stretch. Okay, so you can clearly see there's a big discrepancy between the experimental one. So the experimental one is 1725 per centimeters. This one is 1978 per centimeters. But you now can visualize it. You know what's happening here, and then you can fill in your table. So compound is acetone, active bond pair is the carbon and the oxygen. The carbon and the oxygen is what's vibrating mainly. See, I mean, you can say the CHs. So you can list the CHs are also vibrating. So for example, you see the CO is mainly vibrating primary, and then secondary you'll say the CHs are wagging. So this is a symmetrical stretch, and the CHs are sort of bending. You see there's a little bend in what they are doing. Okay, and that's how you're going to describe this now. Wave number, that wave number is that wave number over there. Calculated wave number is the calculated wave number over there. Description of the bond active pair, that's what I just did there. So in other words, this is symmetric stretch. They say CO is symmetric, CH is like a bend, for example. And you use this figure, also the one in the pre-practical lecture, to give you a suggestion of what is happening. So maybe it's in plane rocking is a better description of what's happening, out of plane wagging, or in plane rocking. So you see those CHs are moving like an in plane rocking. They're doing the same motion as described here, right? Then are they moving the same way? No, they're moving towards one another. So it's actually in plane scissoring, moving towards one another. Yes. Okay. Basically, you just have to spend some time on that. And then you fill in the table, and the last part is visualization of the active mode. And I showed that in the pre-practical lecture how I want you to do that. So essentially, you use little arrows and pluses and minuses, just like here, on the molecule. So you take a screenshot, oops, not that. You take a screenshot of the molecule. So you get something that you take a screenshot with, for example. Oops. Screenshot of the molecule, and then you can switch off the vibrations, take a screenshot of the molecule, or you can go back to the calculations page and you can take a screenshot of the molecule there, and then you can just draw in arrows to show where it is. You can also switch on vectors here and vibrations, and then these vectors will give you an indication. Well, this is not a bad example. Where are the vectors? They are supposed to be on. Let's get a better example. Now you see there's little arrows already on them, but I want you to draw in the arrows because, for example, if you look at this one from there, you're not going to really see those and those. Not that this is necessarily a peak that you can envisage, but anyway. Then of course, just a note, for example, these are the CH stretches. So there's going to be a bunch of them. You see, there's a lot of them. For example, all these 3000 stretches are CH stretches. You don't have to do all of them. Do some of them. Pick the ones that is the easiest for you to explain. It's just for you to get, I just want you to go through the ideas of them, essentially. So 1, 2, 3, 4, 5, 6. So at least always do the half of the stretches that are available to you. So if there's 6 of them, at least show 3 of them. So pick 3 of them that you want to visualize in your table. So in the table over here, then the visualization of the IR active mode. Okay, so I hope that will be quite quick. That's why I also say just do it for the 4 most prominent stretches, because otherwise you'll be busy forever doing it. I want to have grid lines, labeling and whatever. Okay, I think that is a good enough idea. And of course, just go play around with this a bit so long, because you will be using in the computational practical. We'll go through it in more detail in the computational practical, but it should be easy enough to build your molecules for now. All of them are quite easy. You can, for example, start with the benzene to just build the there we go. The what's it? The cyclohexene, and from there onwards should be quite easy enough for you to do. Just click away the ones that you don't want. There's cyclohexene. Yeah, other ones quite easy to make. There aren't any ones that are difficult. There's nitromethanol. Yeah, the rest of them are very easy. You can also use the 2D functionality. The 2D functionality, you can build. What's going on here now? I mean, you can build chains. So you can see, you just click on the chain. And you can build a molecule, and then you switch back to 3D, click optimize, and it will optimize itself. Okay, so I hope this was helpful, and you understand what you need to do, and that you enjoy making all these drawings, because it's going to take some time, but it will be worth it.